In this module, you'll work with some more right triangle trigonometry as another way of viewing what the meaning of sine, cosine, tangent, and so forth are. Now, from the previous module, we did some work with unit circle trigonometry, and our basic idea came down to the following type of triangles, where we had a unit circle, meaning that the hypotenuse was equal to 1, and we had x coordinates and y coordinates with an angle of theta coming off the center of that circle. We defined the trig functions based on the following. We decided that the sine of theta was equal to y, and that the cosine of theta was equal to x, and then later defined the tangent of theta to be y divided by x, because the tangent of theta is the slope. In this module, we want to look at these trig functions from a little different viewpoint. I'm going to extend this sine function and say that the sine is equal to y divided by 1, and that the cosine is equal to x divided by 1. The tangent function is still y divided by x. And now if we look at it from this viewpoint, we have two sides of the three on our triangle. We need to come up with some definitions. From the angle theta, we have a side that's opposite from that angle, and in this case it's the side length of y. So we're going to call all of the y's opposite sides from the angle that we're working with. We also have a side, the 1, which is the hypotenuse. So we're going to call all of the 1's hypotenuse values. And then the third side that's remaining, we're going to call that the adjacent side to the angle. Now I know there are two sides that are really adjacent or next to the angle, but one of them has to be the hypotenuse. So therefore the other one is adjacent. So now if we look at the sine, cosine, and tangent in terms of these three ratios, we see that the sine of theta is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. Now, the value of this is, if we have these definitions, we can use them to find unknown angles and sides within right triangles. We'll go to the next slide for an example. Let's take the example of us having a right triangle with a side length of 10 over here and a 60-degree angle right here. Our question, we want to solve for x. Using the three trig ratios from before, if we let 60 degrees be our reference angle, we see that the 10 side is really the hypotenuse and x is really the adjacent side. So we look back at those three trig ratios and decide that this is the one that's related to the trig function of cosine. Since cosine of theta is equal to the adjacent side divided by the hypotenuse, if we fill in our values, the cosine of 60 degrees is equal to the adjacent side x divided by the hypotenuse, which is 10. Now I have an equation that I can solve for x. It's very easy to solve this for x. I just need to multiply both sides by 10. So 10 times the cosine of 60 degrees is equal to x. And from earlier, in the previous module, we had the cosine of 60 being equal to 1/2. So 10 times 1/2 looks like, in this case, x is equal to 5. Once I have established the fact that x is equal to 5, I can now use some easier geometry to go ahead and find the remaining angle measure and the remaining side. Okay? If I decide to call this angle beta, I really don't need to use any trig to find this, because since I have a triangle, I know that the three angles must add up to 180 degrees. I'm only missing 30 degrees because I already have 90 and 60. So very quickly we see that beta in this problem is 30 degrees. And then if I want to find this remaining side, I'll call it y. I can do that as well. I could use a trig function, or I could use Pythagorean theorem. To me, it seems like Pythagorean theorem will be a little bit easier. I could take 10 squared minus 5 squared and then square root the result to get the value of y. In this case, it looks like the value of y is the square root of 75, which I could also simplify or could find with a trig function. Now, at this time, I'm going to draw another triangle, clear the screen, draw another triangle, and have you do some work to find a missing value from a right triangle. I'll keep it the same orientation for right now. Let's say that we have a 35-degree angle, and we know that this side is 15 and this side is the one we're interested in finding, x. At this point, you should pause your video, spend some time trying to solve this, and when you're ready, click the play button and I'll go through the solution. Alright, hopefully you've come up with the right answer. In this case, we see that the side of 15 is opposite of our reference angle. The side of x is adjacent to our reference angle, so therefore we want to use the tangent definition. So the tangent of theta from earlier was opposite side divided by adjacent side. If we substitute in all of our values, we have the tangent of 35 degrees equal to 15 divided by x. I'll need to do a little bit of algebra to solve this, but not too much. I can cross multiply both sides by x. And remembering that tangent of 35 is just a value that I can get from plugging tangent of 35 into my calculator, I can divide that from both sides. So in this case, x equals 15 divided by whatever the value of tangent of 35 is. And if I plug this into my calculator, I come up with roughly 21.4 for the length of side x. The next thing for us to consider is, what if we have a triangle that looks like this? Still a right triangle, and I have my angle theta down here, but I have side lengths of 6 and 8. And I'm interested in solving for the angle this time. Now, the last examples we were given the angle measure and that allowed us to solve for some side lengths, but this time I really don't need trig to solve for any side lengths. I could just use Pythagorean theorem to find that hypotenuse. So how can I use trig functions to find an angle measure? Well, it's really not too hard. We still start with the same approach. I know I have in this problem the opposite side 6 and the adjacent side is 8, so I start with the tangent function again. Tangent of theta, opposite over adjacent, so 6 divided by 8. Now, in this example, I need to get rid of the tangent function so that theta is on a side by itself. The way that we are able to remove a trig function like this is to take the inverse tangent of both sides. I can't squeeze it quite in there, so I'm just going to write it right here. So what I've got is, on the left side, the inverse tangent of the tangent of theta, and on the right side I have the inverse tangent of 6 over 8, which is 0.75. Now, the purpose of doing this is that the tangent and the inverse tangent functions undo each other, or cancel each other off. So now my value for theta is just the inverse tangent of 0.75. This can be found by punching it into your calculator. All calculators that have a tangent button probably have an inverse tangent button right above it. And if we go through and type that in, that will be the value that we're looking for. In this case, theta is roughly 37 degrees. Now, we have the ability with trig functions and inverse trig functions that no matter what conditions we are given on triangles, if we're given enough information, we can find all the rest of the sides or angles that we're missing. So this is the next step for you. Again, I'm going to give you a problem and have you use trigonometry or some other means of geometry to solve for all the missing sides and angles. In this case, let's say this side is 5, this side is 3, and this side is unknown A. And this will be angle theta and angle alpha. It's your job to solve for A, alpha, and theta. You should pause the video at this time and see if you can apply the knowledge that's been described earlier in this module. Alright, solving for A, alpha, and theta. In this case, I would start by solving for A, although it's not necessary. You can do this in any order. I know the two sides are 3 and 5, so I can use Pythagorean theorem to solve for the remaining side. So 5 squared minus 3 squared, and then square root the answer, and I'll come up, in this case, with A equals 4. 3, 4, 5 is a very common right triangle. And so if you ever recognize that you have two of those numbers as your side lengths, you should be able to recognize the third number that's missing. Now, the angles will take a little bit more work, but let's go ahead and work on them. Let's start with angle theta. Okay. From here, I have now all three sides, 3, 4, and 5, so I can use any of the three trig functions that I want to. Okay. For example, let's just say that I decide to work with the side of 3 and the side of 5. The side of 3 is opposite of my reference angle. The side of 5 is the hypotenuse. So the trig function that I need to work with here is the sine function. So the sine of theta is equal to 3 divided by 5. At this point, I would take the inverse sine of both sides so that it would cancel with the regular sine on the left side. 3 divided by 5 is 0.6, and so the inverse sine of 0.6 will be my answer. And this should look a little familiar. My answer is 37 degrees, and that should remind you from the previous problem that, hey, we had 37 degrees on that question as well. We'll talk about why that is here shortly. In order to solve for alpha, I can use the fact that the sum of the three angles of a triangle are 180 degrees. So alpha is just 180 degrees minus the 37 from theta, minus the 90 from the right angle, and I can see that in this case, alpha should be a roughly 53 degrees. Now, why did this match up? Why did this 37 degrees from theta match up with the 37 degrees from the previous problem? Well, let me redraw the previous problem so we can remind ourselves what it looked like here. The previous problem, we had this situation. Now, if we look at these two triangles and think about them, they're actually similar triangles. If we consider the fact that one of the sides, 3, was doubled to another side of 6, the other leg of the triangle, 4, was doubled to the side length of 8, that makes sense that the angle measures should be the same, because if two triangles are similar to each other, they have the same angle measures in all three locations. So this makes a lot of sense. Alright, one more example to finish up this module. I'm going to give you one more triangle with some missing information and have you use what you've learned so far in this module to solve for some missing values here. Let's call this unknown angle beta up here. Let's call this side A and this side C. Again, pause the video and solve for A, beta, and C on this right triangle. Alright, for this final example here, again, you do not have to solve for it in this order. I usually solve for the easiest thing first. In this case, to me, beta is the easiest value to solve for. And in this case, it has to be 20 degrees because I already have a triangle with a 90 degree and a 70 degree angle, so I'm only missing 20 degrees. Now, to solve for A or C, again, there is no specific order that needs to be followed here. I'll go ahead and pick A, solve for A first. And again, I don't have to necessarily be very picky with the trig function I use. It depends on which reference angle I want to work from. Let's work from the given reference angle of 70 degrees. And if we look at that, A is the opposite side, 6 is the adjacent side, so that tells me I'm going to need to work with the tangent function. So the tangent of 70, this needs to be corrected here. So the tangent of 70 degrees equals A divided by 6, opposite over adjacent. So now if I multiply both sides by 60 and plot this into my calculator, 6 times the tangent of 70 degrees is roughly 16.5. So my side A is 16.5. At this point, again, I have some options. I could use Pythagorean theorem to solve for the unknown side C. I could use another trig function. If I wanted to set up a trig ratio with the 70 degree angle 6 and C, I could use the cosine function. I could say the cosine of 70 equals 6 divided by C, and I could go through and solve for that missing value. In this case, no matter which approach you take, C ends up equaling 17.5. This concludes the module on right triangle trigonometry. The key things to remember from this module, you do need to know that sine is opposite over hypotenuse, cosine of an angle is adjacent over hypotenuse, and tangent of an angle is opposite over adjacent. We can also work with cotangent, secant, and cosecant in this way, but we don't see them as often. One final comment with this module is to be very careful with the following misconception from some students. When working with inverse trig functions, we sometimes write the inverse sine of an angle, but we need to be very careful to recognize that this is not the same thing as 1 over the sine of an angle. Okay, it's a little bit confusing because of the notation in math. We sometimes see something to the negative 1 power, and we think, okay, that means move it to the denominator, to the positive 1 power. But with trig functions, this is not the case. 1 over sine is the same thing as cosecant, but inverse sine is not the same thing as cosecant. If you ever see an inverse on a trig function like inverse sine, that is referring to the fact that you have the side lengths and are trying to work backwards to find the missing angle measure.